Okay. When we talk about chemical kinetics, it's one of the three major concepts and theories that are applied to study of chemical reactions. Now, I frequently tell students that my course is in Chem 2 is a study of chemical reactions. And as I showed you yesterday, this includes the kinetics, equilibrium, and thermodynamics. Kinetics is the rates of reaction. Equilibrium, extent of reaction. Thermodynamics, feasibility of reaction. Like that. Now, in the study of reactions, we all know reactants first go to products. So if you consider, for example, how the concentrations of reactants change as a function of time, as well as the product change as a function of time, what you'll get is a graph. It looks like this in a general context, where the horizontal axis is time, and over here concentration of your reactants and products. So at time 0, how much product do you have? 0. You don't have any product. But at time 0, you're 100% in the reactants. So we'll say that's the reactant concentration. Now, what I'm going to ask you to do is think in terms of horse racing. And in a reaction, the reactants are like horses in a gate before the reaction starts. Yeah, I'm sure you can see that in your mind. Then when we say go, then you mentally open the gates and let the reaction run, so to speak. So what happens when we open the gates? Well, of course, the products are made from the reactants, so you would naturally see a trend that would follow this, like that. At the same time, since we started at 0 with the products, you will see the products concentrations increasing in the same fashion until you have a 0 slope in the reaction trend. And so this would be your product concentrations at time t, and this would be your reactant concentrations at time t. Now, in this graph, you've divided into two parts where the trends go to 0 slope. I'll make that right here. We find the two major concepts of reaction study is between the two halves. For applications on kinetics, we find it to take place in this left region, and we call it the kinetic region. From 0 to here. And then beyond on the right side, where the trends reach 0 slope, this is the equilibrium. And that goes on to wherever, for as long as you want to watch it. So as we go into this, what we're going to be doing is applying the methods that I mentioned yesterday in the introductions in this region. The reason they're separated is that as you take a slope to any point in this curve, you find that no point in the curve has the same slope. So there's a constantly changing slope, but when you get into the equilibrium region, of course, slope equals 0. And so there is really no change in concentration apparently, as it's showing here and of course back here. So those are equilibrium concentrations as they're called. Probably a good example is of course the evaporation of water when you put a lid on the container. If you had a container, let's say water, then molecules would of course evaporate into the vapor phase. But if you covered this container, the number of molecules would maximize and become saturated. Saturate that volume above the water. And so as it becomes saturated, then what happens is molecules will begin to recondense at the same rate that molecules are evaporating. As it's condensing back into, and this is what we call the law of mass action, and is the foundation of any equilibrium study. The rates forward equal the rates in reverse, and hence there's no apparent change in concentration. If you put a jar of water out on the pavement outside, covered it, and came back an hour later in a hot summer day like it is today, the volume would be constant. You would not see a change in that level of water. However, if you remove of course, if you remove the top or the cover, the liquid would eventually evaporate into vapor phase and dissipate into the atmosphere. But this is where all of the next 5 chapters come from, is the realization of what the reaction is doing and where it is in the reactive process. Chemical kinetics. So the kinetic region describes rates of reaction. And that rate of reaction is proportional to what we call a function of a reaction factor. And we mentioned those yesterday in terms of reaction factors. CANTC, referring to concentration changes, surface area changes, nature or the chemical structure, temperature effects, and catalytic effects. So our job is to determine how concentration affects reaction rates or area or any of these factors. So what we do is we have a reference reaction reactants goes to products, and this reference reaction gives rate 1. Okay? Then we apply change, and then we get our first experimental reaction. And so this gives a reaction rate number 2. And so the change in this rate of reaction from case 1 to case 2 defines what we call the rate trend of the reaction. Let me make that a little. And we call those order of reaction. And that's where we are in our study. And we were talking yesterday about concentration effects. And so how does changing concentration affect the rates of reaction, and how do we identify certain rate trends or orders of reaction? Okay, concentration effects. There are 4 problem types, as we mentioned yesterday, on the concepts that you need to be able to deal with. The first 2 are relatively straightforward. The experimental, you'll see in a minute, is a little more involved. And of course, you have the integrated rate laws, which we'll look at shortly. Anyway, rate averaging. And then we have rate as function of coefficients, and balanced standard equation, experimental rate laws, or just rate laws. I call it experimental. And integrated rate laws. Okay, so yesterday we showed you that rate averaging is just simply the application of the data to the definition of chemical rate of reaction, which is a change in concentration, molar concentration that is, over change in time. And we worked a couple of problems, or one problem at least, on that. So it's just really straightforward in terms of you have concentration final minus concentration initial over time, that or change in time, and it is represented typically in terms of an absolute value. So we can put the 2 bars on either side of the expression like that, because in general opinion, actually a rate at a given point in that trend reaction where the concentrations are changing as a function of time, it's called, if you take one point in that curve, it's called an instantaneous rate of reaction. I'll tell you what, I'm going to draw that and make a note for you. So if we just look at the reactants, concentration changes over time, like this, and if you picked a point right there and calculated the rate, see here's a time and here's a concentration C at time t, and you have your time value there. And so the rate equals that concentration number at that time over time. And what I'm trying to say here in this rate averaging is what you're talking about in the description of rates is what they call an instantaneous rate. So as far as terminology, and that's quite important as you go through, because as you talk about the instantaneous rate, we're really talking about the slope of the line that touches that point. And as you move to, say, point time 2, so call that time 1, and this one time 2, of course the slope of the line is changing. And so the instantaneous rate concentration 2 just 1, okay, would be different than the concentration over time 1. Okay, and so it's important to realize that what you're talking about is a specific number as you go along that curve, and it's not positive or negative, but it is a value that defines movement or velocity without giving signage. Yeah, the rate of reaction is slowing down, but it's slower here than it is in the first dot. But identifying velocities in that context, how do you apply a sign? If you compare velocities of this one, V1 against the V2, change in velocity over time is not speed. It's acceleration, and that's something else. Yeah? You can have a positive negative acceleration, but not a positive negative velocity. Now that's an argumentative point that you'll run into if you ever work in this area. Rate or reaction rates proportional to equation coefficients. And you saw us use the simple equations yesterday. I'll do another one real quick here. Bound to have one. When you consider a balanced equation, of course, it's obvious that the coefficients in the substances are different in the balanced equation. They indicate change is different, or the rate of consumption, the rate of production is as a comparison between two of the substances is different. So if we compare the rate of ammonia to the rate of oxygen, yeah, you can do that. But the rate of ammonia, as we said yesterday, as a change in time, is greater, in this case, less than the change in O2 as a function of time, because the coefficient of oxygen is larger than the coefficient of ammonia. But in problems, what you will be given is one of the rates, and so and you can get the other rate that of interest that you are relating to, and you can set that equal, but you have to swap the coefficients. So to equate these two, as we showed you, doesn't hurt to review. Five, being associated with oxygen in the equation, needs to be put as a number coefficient to, if you would, to the rate of ammonia change. And the 4 needs to be made a coefficient to the oxygen change. Then whatever value the problem gives you, say it gives you oxygen, assume rate of O2 used equals 0.012 molar per second, like that. Now you can calculate the ammonia. Is 4/5 of the change in O2. And it gives you a 0.0096 molar per second rate based on that relationship, given one against the other. I don't know where that came from. Is that what your question was? Okay, thank you. But I think if you reviewed yesterday's notes and you understand what I'm saying in these relationships, you won't have any trouble, because that's what I'm going to give you as an equation and one of the rates, and you figure the unknown rate that's in the relationship. Also make a note that the setup of this type of problem is only between pairs. It will not give you 3 of them to build some kind of equation. It's always in pairs to set up and swap the coefficients and solve for the unknown. Substitute, you're there. So practice a couple of them, make sure you're comfortable, and if you have any questions, certainly let me know. The experimental rate laws as a function of concentration is what we're trying to derive. And earlier I pointed out that in working with the rate laws in experimental format, you establish a reference or control, is what it's called, reaction rate, and then double or triple or cut in half or whatever you do with the concentration value, and then see how the rate changes relative to that, to the first one, the control rate of reaction. So what we're going to do is now one of the things about this is the rate law that's written is always written in terms of the reactant side of the equation. Now what this means is you'll have a problem that will ask you what is the rate law for the following reaction. It gives you a bunch of data. Well, in the reaction, say given hypothetically A coefficient plus B goes to products. So this would be an empirical type of relationship. To write the rate law expression, again, only in terms of the reactants. Now you may use the product in an experiment, and that's what I'll show you in the demo Monday. You may use the product's concentration changes in monitoring, but when you write the final rate law, it's always in terms of the reactants. And that's written like this, and they're all written the same way. So whatever reaction you get, do this. rate equals, that's a start, and then you put a lowercase k, which is called the rate constant. Now, and then put times the concentration of the first reagent, A, times the concentration second reagent, B, raised to arbitrary powers like X and Y. In the kinetic region, the X and Y are not the coefficients in the reaction, balanced reaction. However, in the equilibrium region, they will be, and we'll show you that Monday when we get to equilibrium. But here, these are referred to as orders of reaction with respect to the reagent component or reactant component. That is to say, X is the order of reaction. The phrase is very important here. X is the order of reaction with respect to A. Y is the order of reaction with respect to B. So that's the phraseology as well as the meaning of what that exponent is. You already know what brackets A, brackets B mean. It's molarity. Okay, now again, the rate constant is a number, numerical, it's a proportionality constant when it's all boiled down. But we call the rate constant the speedometer of the reaction. So really people will refer, while rate is a definitive number, value, but rate is dependent on concentrations over here. But this is a constant for whatever concentrations, because if you solve for K, it's the same for whatever concentration you put in there. And that's a constant. So people will refer to if they're working with a given reaction, refer to that reaction's rate constant more than they'll refer to the rate. But if they want a more definitive rate based on concentration, they'll substitute that constant times whatever concentration values that they're using. So this gives, I say, speed of reaction. And it's not an official in that context, but yes, it is. That everybody refers to it in that context. Okay. Okay, first of all, one must find a component of the reaction that can be monitored relative to concentration. Understand what I didn't say. I've been teaching you that writing rate law expressions is always in terms of the reactants. But this, in determining experimental rate law, you can use any component that you can monitor in the reaction. For example, the demo I'm going to show you on Monday is the savolysis of what we call a T-butyl halide. And one example is T-butyl butyl chloride. And it has a structure sorry. It looks like this. That's the T-butyl chloride. But what we do is condense it T-butyl chloride like that, and then put it in the reaction and show you how it works. Well, if I take T-butyl chloride and react it with water, in other words, I'll take a quantity, this comes in liquid form, and you maybe take a milliliter of it and inject it into, say, 50 milliliters of water. And now we'll repeat some of this stuff Monday. What this does is it forms T-butyl alcohol and hydrochloric acid, HCl. What happens is OH group from water, because that ionizes, the OH group is strong enough to replace the chloride. And so the chloride would come off as a leaving group and connect up with the hydrogen that we left behind from the OH. And so that ultimately gives you the HCl. Well, the rate law for this, the rate law expression, is simply rate equals K onto T-butyl chloride raised to the X power and H2O raised to the Y power, like that in terms of the reactants. But the issue is we cannot monitor either one of these components, but we can monitor the production of hydrochloric acid, because hydrochloric acid, as it's produced in a water environment, will cause an increase in pH value. Before we inject the T-butyl chloride, pH is 7 for water, because we're going to put, neutral water in. But after injection, you'll find the pH drops to about 3. And low pHs, as you recall, maybe from previous courses, defines acidic mediums, and we'll learn more about where that comes from. We'll get to acid-base equilibrium. So what I'm monitoring here is a component in the reaction and translating it into what the reactant is doing. And this gives an concentration changes, say, of the T-butyl chloride. You'll in a minute you'll show how H2O will fall out of this reaction. But right now, what I've taught you was, here's the rate expression. The rate law expression is this. But we can monitor anything and translate that, whatever we monitor, in terms of whatever's on the reactant side. So this is one of the things I want you to understand about how the experimental process works. Also given, say, rate law, say rate equals K onto A raised to the X power and B raised to the Y power. And so what we're going to do is change the A and B as we go through, and let's see what happens. The values that you will be trying to obtain in your experimental work will be the x, the y, and the k. So this is the focal point of the experiment or the data that you have to evaluate. So what I'm telling you is that the only way to determine k, x, and y is by experimental method. There is no method of calculation to determine that in terms of rate expressions. So x, y, and k values can only be determined by experiment. Experimental observation. Comparing reaction rates. So this is kind of the foundation of what we're about to do, even though it might be abstract to you right now. In problem type 1, where we had the rate averaging, problem 2, coefficients, yeah, you took data and plugged it into formulas that you already had. But here you can't do that. You have to extract experimental data values and apply it in a certain way to determine what x, y, and k are in the rate law expression. I don't think there's anything out here. Okay. What we're going to do is we're going to construct a simple hypothetical reaction and show you how to develop or identify x and y first, and then finally how to get the k value. Okay. So now you're given a reaction. A goes to products. Very simple, it's only one component, decomp, and produces products. First thing you do is write what we call the empirical rate expression. Writing the empirical rate expression for the reaction, again, is in terms of the reactant, so we simply write rate is equal to k times the concentration of A raised to the x power, since there's only one component of the reactant side. Now what we want to do is change the concentration of A lowercase a is a number, okay, value. Then we'll double it and then triple it and so forth as many times as we kind of wish to change it and see what the trend is. So this will be, of course, the reference reaction, of course, or control, as some people call it. The reference reaction, and then when you double the reaction, this is your experimental value that you're comparing to the control. So we start out with, say, rate 1, we'll call that R1 is equal to K times A raised to the X power. And then we'll have R2 equal K, and then we'll double the concentration at the same X value. So what we're looking at is how does the reaction type change assuming whatever X is. X can be a whole number, a negative number, or fraction. Now I'm just going to use positive whole numbers for the moment, and we'll translate into negatives and fractions some other time. Okay, and of course rate 3 would be K onto 3A raised to the X power. So we want to test 1, 2, and 3. We want to test X equals 0 power, 1 power, 2 power, maybe a 3 power. So that's what we want to test and see empirically what the result is. Now I'll come up here like this. So we're starting with, let's see what the trend is if everything's 0 power in our rate expression. So we'll take rate 1 equals K onto A raised to the 0 power. Rate 2 will be KA, 2A, excuse me, 2A raised to the 0 power. And rate 3, K3A raised to the 0 power. Well, we know that any number raised to the 0 power is 1, so all of these would go to 1, and you're left only with your rate constant all the way down. This is called a zero-order reaction. Change in concentration yields no rate change, no change in rate. So when we were looking at the T-butyl halide added into water, and it's been shown, and there's no point in experimentally going through all of that, that it doesn't matter how much water you have, the reaction rate regardless will remain the same. So the water in the T-butyl, say chloride reaction goes to 0. I should have written it out in the rate law. Rate equals K T-butyl halide to the X, H2O to the Y. Well, Y is 0. So what this does, this goes to a 1. And so your rate law will reduce to K onto T-butyl halide raised to the X power, and all you have to do is get K and X in the final analysis. So this is what a zero-order reaction says. Okay, now a first-order reaction is one where we assume a 1 as the exponential value. We've got reaction where concentration A, as you recall, is A, 2A, 3A, and so forth. Well, rate 1 is K times A to the first power, and that's a reference. And so we want to see how everything changes relative to that one. So rate 2 is the rate constant times 2A raised to the first power. Rate 3 is K3A raised to the first power, and so forth. 4A raised to the first power. And so A to the first is A, so that's Ka. 2A raised to the first is 2A, so this gives us 2Ka. And 3A to the first power gives us 3Ka. So what we're seeing between these two is if you double concentration, rate doubles. If you triple concentration, rate triples. So this is kind of what we call a one-to-one change. Rate concentration, double rate, double concentration, double rate, triple concentration, triple rate, and so forth. Well, what this shows up as in a plot of concentration versus rate is for C1, concentration 1, or let's just go A, and then let me move it over some. A, 1, 2, 3, 4, 1, 2, 3, 4, 2A, 1, 2, 3, 4, 3A, 1, 2, 3, 4. Kind of give you some perspective, and so forth like that. Well, and so say rate A is right here. So this is rate 1. 2A would double that, so it's 2, and then we'll go 2, 1, 2 to there. And then this would triple it, 1, 2, 1, 2, and 1, 2. You notice the trend. And this is quadruple it, 1, 2, 1, 2, 1, 2, 1, 2, 1, 2, and then we'll find our cells right up there. So you can see the linear trend generated for a first order reaction. A second order reaction, of course, is rate equals K onto the concentration raised to the second power, and we do the same thing. Okay, so again, A is going to be A, 2A, 3A, and so forth. So rate 1 is K onto A squared, and that's our reference. And so rate 2 is K 2A squared, and rate 3 is K 3A squared. If you want to go to rate 4, K 4A squared. So what happens if the reaction is a second order reaction and we change concentrations? Okay, so this gives you a Ka squared, but when you go from double the concentration, 2A becomes 4A squared, and so we have a 4 times increase in reaction rate. And if you go to 3A, 3 and 3 is 9, so we have 9 Ka squared, and so this is a 9 times increase in reaction rate. This is rate on the end down there. So now again, this is your reference. You always have to establish a reference somewhere, and then you look at the change and see how big the change is, and then you assign the order of reaction, like the X or the Y would then be, in this case, if you saw this trend, then you would assign a 2 to the exponent, and it would be the second order, and of course 16 Ka squared, and again it's a 16 times increase in reaction rate. So now you won't see any higher orders of reaction, except to say, how do you get the overall order of reaction? What these are showing is just the effect on one component, or a single component reactant decomposing into products. But your order of reaction for overall, if you have a multi-component reaction, say rate equals K A to the X power B to the Y power, it's very easy. The overall order is the sum of the exponents. In this case, X plus Y. Now, that's if you have A is to the second power and B is to the first power, your overall order would be 3. So you won't have to use the problems we're fixing to work types for anything above second order. but you may have to get the overall order after you get each one of the values. Determining order of reaction. A zero order reaction gives a constant equals K, or no change in reaction rate. A first order reaction gives a linear change in reaction rate. That is to say, you double concentration, you double rate, triple concentration, triple rate. And second order reaction shows an exponential rate trend. Double A to 2A, that'll give you a 4x increase in rate. A to 3A, it gives you a 9 times increase in rate. And 4A, 16 times, and so forth. Okay, so what am I telling you to do? You have to relate this to the problems we're going to work right now. So, from the worksheet, you have this problem right here. So, determine the rate law for this reaction based on this experimental data. So, what you do is you hold one constant and vary the other one. Then when you finish that one, you hold that one constant and vary the one you just held constant, and then see what the reaction rate changes are. So what like in this, you notice that this doesn't change in concentration. So what I'm telling you is pick a pair of concentrations that are the same for one of the components, yet you notice that this is 2 times increase in concentration. And then when you determine the rate change, look at this. This is your reference, of course. Then you can say, okay, the rate increased by whatever. And so this is a first order, second order, whatever order reaction. So we take 0.468 divided by 0.117, and we see the differential here is 4. That means it went, when you double concentration here, the reaction rate jumped 4 times. Okay, that means you have a second order reaction. So when you write the rate expression, which includes the reactants, then, and we don't know what Cl2 is yet, we want to assign a 2 there. See how I did that? That's why I say you have to remember what the trend change is to make your assignment. Then we hold this one constant, the NO constant, and vary the chloride. So I look down here and I see a doubling of concentration on the chloride, while at the same time we keep this constant right here. So when we double this concentration, we see a change here. So what is that? That looks like a 2x to me. Yeah, I did check it. I know. I'm sure it is. 1.04. Yeah, 2. 2 times increase. So we say this is a first order So we want to assign a 1 right there. Okay, so the only thing left is determining what K is. So the K is a rate constant, and as I mentioned earlier, K is always the same for every experiment you run. Every one of these rows of data give you the same number of K. I can pick any row in here, apply it to this expression, and it'll give you the same number. You test it later. I'll just do 1 or maybe 2. Say K from the row 1 here. Well, we solve this expression for K. This is rate over NO squared and CL2 to the first power. And in row 1, we have a 0.117 molar per second divided by 0.1 squared in this one. And CL2 is to the first power. And 1, 2, 3, that's molar cubed out of that collection. And so this will reduce to $117. Now this will go to molar to the minus 3, add back 1, so that's molar to the minus 2 times seconds, molar squared, I'm sorry. No, that is right. Molar to the minus 2 and seconds to the minus 1. This is a proportionality constant, like I mentioned earlier, and so it is going to have some squirrely units associated with that value. So your numerical rate expression is therefore rate equals, if I can move that up, rate is equal to 117 molar to minus 2 seconds to the minus 1 NO squared CL2 to the first power. You don't have to put anything up there. If there's 0 power, it wouldn't be there. So this is the objective of that kind of problem in working these experimental rate law problems. We're working over. So notice each one of them will give you a set of data, and you hold one constant and vary the other one. And then when you finish that one, go back and hold that one constant and vary the other one that you started to hold constant. Okay. So we begin by writing the empirical rate expression, and that's NO to the X power and O2 to the Y power. And then we assign, we pick one to hold constant, one to vary. So looking at this, looks like this is a 2x here, while this is a constant. And so what is the change between these two? So you go O241 to that. So that's the 4 times increase. So X is now a 2. And so we hold this one constant, as you see, that one and that one constant, and we have a change 2 to 5, that's the 2x. And so from the 0281 is what we're comparing to the 056 right there. Looks like a double 2x, so y is equal to 1. So now we have rate equals k NO squared O2 to the first power, and k is equal to rate over NO squared and O2. So we pick a row, pick number 3 if you wanted to. K then is 0.0561 molar per second divided by 0.0121 squared and 0.0506 to the first power, and that's molar cubed in the denominator. And so that would give us 0.0121 squared times 0.0506 equals reciprocal times 0.0561 over 0.56. And so I get 7573, and that'll be molar to the minus 2, seconds to the minus 1. So our numerical rate expression is 7573 molar to minus 2 seconds minus 1 NO squared and O2 to the first power. And so you see the, oops, too far. That's how you deal with those kind of reactions. Are essentially the decay process. So in essence, what we're ultimately looking at here, let me see if I can give you a good example. In the integrated rate laws, we have rate, by definition, is a change in concentration over change in time. And for, say, a reaction, A goes to products, we have rate is equal to change in, say, A over change in time, which is by definition. When we talk about these, what we want to do is integrate the rate expression over here, and this represents a differential issue in that rate is equal to a derivative of A, is what it's called, over change in time, like that. And each one of these is applied to, say, first, second, third order. So a zero order reaction would have a rate expression to equal dA over change in T, and then you remember, if it's zero order, what's the rate change? It's a constant, and these typically it's assigned a K value. If it's a first order reaction, rate is dA over, it should be dt, not delta T, is equal to just however you change the concentration of A. So it'd be K times the concentration of A as you go along in this. And a second order reaction to be squared. Rate equals dA over dt to equal Ka second order. Well, this one here would be, of course, A raised to the 0 power, and that would have given you a constant. So these are your setups. Now what you need to do in getting the expressions for what they call the integrated rate laws is you solve this in the following way. Let's see. Zero order goes to dA to equal K dt. So I'll change that to dt. We multiply both sides, and this just simply moves to the other side. First order goes to dA, which is equal to K A dt, like that. Okay, and actually this will go to dA over A to equal K dt. And then in second order is dA to equal K A squared dt, and that goes to, and ultimately goes to dA over A squared to equal K dt. So the integrated rate laws, now why am I going through all this? Because the phraseology of integrated rate laws is so widely used in scientific research. I seem to have, or I assumed, an obligation to at least show you where all this comes from. Now, in working problems, I'll probably limit it to one of the orders of reaction, like the first order reaction only. But to see where these come from is, in my humble opinion, very important in your learning curve. So when I say integration, now you simply come over here and you integrate the derivatives, as we have always done in your math courses, which would be this and that. So what is the outcome of these integrations of the expressions shown? So zero order, if we integrate this, is a constant. So let me show you them. So the integral of dA is A, concentration of A, which is initially A naught, whatever concentration it is, minus KT. KT is of course, dt. Integration of just dt is t. First order expression gives an A onto A naught e to the minus KT, like that. And the second order gives you A wherever it's going to, get that expression. Actually, it's not that, it's 1 over A to equal 1 over A naught, when it's all said and done, plus the KT. So these are what we call the integrated rate laws. Okay, so now you've seen where they come from. What do we do with them? These are used to determine what future concentrations are, starting with an initial concentration over time. So if you look at this is a concentration versus time relationship in a chemical reaction. So in the initial stages of what I've shown you, and since you're working with the reactant side over time and concentration, this is 100% of the reactant concentration, and these apply to a reaction goes to products. So whatever that concentration is going to products. So if you have a zero order reaction, it would define that trend. If you had a first order, it defines that trend. Or a second order, it defines whatever that second order trend is from the time concentration standpoint. Let's look at this first order reaction and some problems that go with it. I'm sitting here thinking, I'll just keep it to first order because that's probably most widely used in scientific work. And there's one little, well, I'll show you in a minute. The first order decay equation is A equals A naught E to the minus KT. Like this, where A naught is the initial concentration, A is the final concentration, and it's important to note here that when we talk about final concentration, it's the amount remaining. K is your rate constant, and T is the time over which you're trying to determine things. Okay, a problem would be like, well, let me show you. Let me show you one other thing too that you're going to need. So what this describes, as I mentioned, is the first order rate trend, which goes along this dotted line. So when you start, and that's concentration. So the object of the problems is to determine what concentration is over time. And one type of problem is what we call half-life. So this is the initial concentration, say. When you cut this in half, I got 1, 2, 3, 4, 5, 6, 7, 1, 2, 3 and a half. Say right here, this would be the original concentration over 2. And if you extrapolate this to the axis and then straight down to the time axis, this is called the half-life. The first half-life. If you cut that in half, I'm going to condense that a little bit. Cut that in half, that'd be A naught. Half of this one would be over 4, right here. And so extrapolating that to the axis and coming down to here, you'd be, this is 1/2 number 2, or the second half-life. That's what it's called. Now, one rule that you want to remember in first order type problems, the half-life, first half-life, and the second half-life, that is starting from here to, second at AO over 2 to AO over 4, the time frame in here, actually even cutting this one, T3, are the constant. The half-life intervals for first order reactions are constant. That is, they're all the same. Very important rule that you're going to need. Now, if we take the half-life expression, I'm just going to use A. They're all molar concentrations or percent concentrations. A equals A sub O E to the minus KT. Okay? What is the expression if we cut the initial concentration in half? What would be over here? That would be A naught over 2. So if A goes to A naught over 2, we have this expression. Okay? Now I can divide both sides of this, and all I'll have is 1/2. equals e to the minus kt. Now, what I can do is take the reciprocal of the entire equation. You can do anything you want as long as you do it to both sides. So reciprocal gets you 2 to equal e to the minus kt. And so I can take the logarithm of both sides. This is a classic development. So it's ln of 2 to equal ln of e to the minus kt, and that's equal to minus kt. Well, the ln of 2 is 0.693, and that's equal to a minus kt, and since t at this point is the half-life, you now have a half-life expression. So actually you have two expressions here that you will need. This gives you a k to equal 0.693 over the half. Oh, that's positive now. That becomes, I take the reciprocal, that becomes positive. Sorry. Over t to the 1/2, or t to the 1/2 equals 0.693 over the k value. Okay, so I'm giving you a lot. What do you remember? Okay, what are you going to have to use and remember? A equals a sub o e to the minus kt, and we're fixing to work problems around that. And your 0.693 equals kt to the 1/2, and this is your half-life. So this is only two equations you got to memorize and use in your test questions or your quizzes or whatever I did. Now that, I know I went through a lot getting to this point, but that's the nature of the beast in this case. Okay. One that says sulfuryl chloride and one that says ethyl chloride here. Both of these are first order reaction type problems. Okay. Sulfuryl chloride, SO2Cl2, decomposes when heating according to this expression. In that format. In an experiment, the initial concentration of sulfuryl chloride was given to be 0.0248 mole per liter, or molar, however you want to write it. If the rate constant K is given to be 2.2 times 10 to the minus 5 seconds to the minus 1, or per second, either way, however you want, that's the units on it. What's the concentration of sulfuryl chloride after 2 hours? A final after 2 hours is the question, and it's a first order reaction. So essentially we want to apply this data to the first order decay equation and solve for T. So A equals A sub O E to the minus KT, like this. And so you've got A and A sub O. So, you've got A sub O, but we need to find out what A final is right here. So A final is equal to A sub O, 0.0248, I'm going to change that to molar, times E to the minus, I'll bracket this, 2.2 times 10 to the minus 5 per second, and we're looking for T of 2 hours. Well, 2 hours can't be used here because your constant is in seconds. So 2 hours is equal to 2 hours times 3,600 seconds per hour. Hours drop out, 7,200 seconds. So this needs to be substituted in there because of the rate constant is in seconds also. Well, I'm not going to change the rate constant per hour, but anyway, the final concentration now is 0.0248 molar, e to the minus 2.2 times 10 to the minus 5 seconds units will drop out, and 7,200, and that will give us, move that up a little bit. Now this portion of the calculation is the concentration reduction factor, is what some people call it. So that's kind of a phraseology issue there. Yes. So now I would suggest, if you haven't worked these before, when you set up your exponential values, be sure to bracket them off so you won't misinterpret the signage and how it's applied. Okay, so that's 2.2 times 10 to the minus 5 times 7,200. And that has a negative value. I want to take the base E, so this would now be 0.0248 molar times 0.854. So this reduction factor is, say, 85.4% of the original amount is what's remaining. So that's 0.0248 times 0.854, and so that will give us 0.021 molar of the S2OCl2, I guess it wouldn't. Yeah, 2 remaining. Now, it's important to keep that in mind in the remaining thing, because problems will come to you. 75% was consumed. What's the this, that, and other question? Well, it's not, the problem doesn't apply to what's consumed. When you apply the equations, though, you need to apply what remains, and that would be 25%. If they say 75% was consumed, what you apply to this equation would be 25%, 100 minus 75. So maybe they've got one in here, looks like that. I'll find one if I don't. That's all they ask in that one. We're given a reaction as ethylene and hydrochloric acid in the gas form. So that's not, that's a byproduct. Okay. The reaction is first order. In an experiment, the initial concentration of the ethyl chloride was 0.00100 molar. After heating it for 500 degrees for 155 seconds, the concentration was reduced to 0.0067. So A final is 0.00067 molar. What's the concentration of ethyl chloride after 256 seconds? Is the central question here. Now, to get this, what do you need? Well, what's the concentration final at 256 seconds is A naught E to the minus KT, where T is 256. So we have the A naught, but we don't have the K value in here. what we have to do is determine the K value from the first part up here. And then apply it to the 256 in there. So taking the data in the part 1 here, A equals A naught e to the minus kt, solving for K, you'll find, and this is, you can just, if you don't know how to derive all this, it comes out ln of A over A naught over minus t times. It's just an expression. So if you take this, that's your first order decay expression, and you will get that. So we can now calculate K for our problem, which is ln of 0.00067 over 0.0010, and that's over the time minus 155. It'll come out seconds to minus 1. So 0.0067 divided by 0.001, take the logarithm of that, divided by 155, and I get here for 6.3 times 10 to the minus 7 seconds to the minus 1. So there's your rate constant. Now that is now applied to the second with the time of 256 seconds here. So your final at 256 seconds now is 0.0010 molar e to the minus 6.3 times 10 to the minus 7 seconds to minus 1 times 256 seconds. Seconds will drop out, and so solving that, so that's 0.0010 molar, and the reduction factor is 0.9998. I just drag it out 1. So it didn't go down much, did it? Well, 0.99 molar after 256. Boy, that seemed like almost no change. Yeah, I did that. That's right. 256. We'll do that. 6.3 times 10 to the minus 7 times 256 equals that. Need to change that to a negative. E to the x. Yeah. Okay, it is 0.9998. So it didn't look like it dropped very much in 256 seconds, in my opinion. Did I pick up the right data? Yeah. I expect a bigger drop in some of these problems, but anyway, that's how you do it. Yeah, this one gives you a reaction that's they want to know how much is left after first half-life, second half-life, and so forth. So if you're given reaction is a chrome 3 plus thiocyanate goes to chrome thio plus 2. What's the half-life in hours? All right, the first order and the rate constant K is 2 times 10 to the minus 6 seconds to the minus 1, what's the half-life, and how many hours would be required for the initial concentration to decrease to 25%, 12.5%, 6.5%, 6.25%, and 3.125. Okay, in a first order reaction, remember half-life is constant and it's given by 0.693 over whatever the rate constant is. You memorize that expression I gave you. Said there are two formulas you need to work with. And so this would be 0.693 over 2 times 10 to the minus 6, and that'll come out in seconds. Not just seconds. And so that gives you 3.5 times 10 to the 5th. Seconds in the half-life, so it takes that long. So what that means is, if this is a first order decay, we'll follow a trend like this as a function of time and concentration, like that. And this is your initial concentration, and of course 1, 2, 3, 4, 5, 6, 7, 8, 9, 1, 2, 3, 4.5. This would be A naught over 2, first half-life. Second half-life, A naught over 4, and then third half-life, that's A naught over 6, and then your fourth half-life, A naught over 8. That's supposed to be look like a 6 right there. So you can see how it kind of squeezes down exponentially as you go. But understand, each one of these is constant. So here's the first half-life is 3.5 times 10 to the 5th seconds. This is 50% remaining. Here is 25%, half of the 50 remaining, and that's 2 half-lives. So that would give you 2 times 3.5 times 10 to the 5th to get from the start to that point. And whatever the rest of them are, let's see, 12.5, half of that one, and then half again. So you'd have 3 times 3.5 and 4 times 3.5 times 10 to the 5th. And all of them are in seconds, of course. So each bracket of half-life is equal in getting to that next level. But if they're asking you for the total amount of time from the initial start of the reaction to whatever's left, then you take multiples of those half-life brackets. Now, one type of problem that you'll run into is radioactive decay. Now, this is kind of a neat factoid for you. All radioactive decay is first order. That is, you can apply the first order decay equation, A equals A sub O e to the minus KT. And it is through this that you get radio dating of organic artifacts as well as inorganic artifacts by determining whatever the K value is for that decay system. And for organics, it's usually a carbon 14 to carbon 12 ratio for radio dating of organic artifacts. You, me, and living tissues, regardless whether it's animal or plant, have a carbon 14, carbon 12 ratio of 1. But upon death, the carbon 12 carbon 14 begins to decay. Its concentration begins to decrease. So for non-living tissue, carbon 14 is less than carbon 12, and everything carbon 12 would have been what is normally considered the living tissue number, concentration, or activity is what radioactivity. So when something dies, okay, it's assumed to have an activity, what we call AO, and everybody knows what that is, so to speak. But then they take samples and run it through radio dating instruments, and they find out what the activity of the carbon 14 is, and that ratio is applied into this equation where and then you can use the expression T, which is derived out of this, is ln of carbon 14 over carbon 12, that ratio over the the rate constant for that carbon 12 decay. And so this tells you the age of the artifact. And K, I don't remember what it is. So if you're given that, let's assume the carbon 14 to carbon 12 ratio is 65% of original amount. That is, you are reduced by a matter of 100 minus 65. So the age would be ln 65 over 100. See, 100 would be the total amount. And minus 57.14, it all comes out in years. So instruments will measure the carbon 14 very easily. You have very sophisticated instruments and technology today. And so that's 0.65 natural log divided by 57.14, and I missed something. 65% decay. That's a 0.65 remaining. I get that should be 0.043, and oh, that's the half-life. Excuse me. That's what my problem is. I know. K is 0.693 over half-life. No wonder I was getting weird numbers. 693 over 57.14, and that's years to the minus 1. That's what we put in that expression. There. Hang on. There we go. So that's 1.2 times 10 to the minus 4 years to minus 1, so that's a minus 1.2 times 10 to the minus 4. All this will come out in years. We got right. Times 0.43, and so that's 45 years. Whatever the artifact is that you're measuring, and so they've measured stuff, I don't know, many thousands of years just from organic tissues that remain, bone fragments and what have you, any carbon datings. But that's one I wanted to show you how that application was associated with first order decay. We move now into reaction rates as a function of temperature in our acronym that we gave you before, the CANTC, concentration, area, nature. Now we're in temperature, and we want to go to catalyst. But this is the one that it's explained in terms of what we call the kinetic molecular theory. The kinetic molecular theory is a micro level analysis. That is, when we say micro versus macro, micro refers to the effect of particle level behavior. Or on the atomic level or the molecular level when we describe rates of reaction. And in doing so, when we describe rates of reaction on the atomic molecular levels, what we're talking about, as you can see in the outline, is a thing called the collision theory and transition state theories that describe what's going on in a chemical reaction. So theories that we're going to look at are the collision theory, and the transition state theory, which comes out of the collision theory. It is based upon a probability and statistics analysis, and in that analysis there is a thing called the Maxwell-Boltzmann distribution curve. And what that means, it's the plot on the average of energies of particles relative to the number of let me say it a different way. It's the energy of particles as a function of how many particles you have. That is, sigma, which is the symbol, is the number of particles. And on the horizontal axis you have either, and they're same, energy or velocity. Energy or velocity factors, like the particles in this room. Every particle has a certain amount of energy in it, internal energy as it's called. But that internal energy is different for all the particles. Some of them have high energy, some of them have low energies, and the Maxwell distribution curve explains that in this way. So if you plotted that, the mathematics generates a curve that looks like this. A bell curve looking graphic. And that is taken to be at temperature 1. And some of the things that exist in this curve is Here is what we call the root mean square speed of particles. If you're plotting in velocities, that would be the highest peak, well, use your imagination, highest peak in that curve, and it's also the median of the energy content of particles in that curve. Now, what is needed is for these particles, say in a reaction environment, to undergo collision and reaction and so forth. And so we found ourselves, if we increase the temperature of this collection of particles, what happens is you see the curve shift, where a number of the particles will now start shifting to the right in this curve at a higher temperature. And you continue to do that where you're getting many of the particles, T3 and so forth. Eventually you can get them all to the right. Well, what is important in here is a line, I'll make it in color here, that represents what we call the activation energy. I'm going to put it out here. For a set of particles to react, they must have enough energy to be at or above the activation energy. That's an absolute law in terms of chemical reactions. Energy must be at or above that blue line for all the particles. So hence, justification for, say, heating a reaction environment until it starts producing products. And then it may not produce a 100% yield for you. Action factors. Now, what reaction factors are a set of events that must occur in order to produce products. And you must have all four of these events, which are four, come together simultaneously. And the greatest probability of those reaction factors coming together simultaneously is at the activation energy. These reaction factors, and don't get them mixed up with rate factors, different, but it looks kind of the same, is C, E, N, T. Help you remember. Well, concentration, again, but E stands for effective collisions. And then N, nature, which means naturally reacting reagents, and the proper activation temperature. These four factors must come together simultaneously to produce products. And like I said, the greatest probability of 4 reaction factors occurring simultaneously is at the activation energy in the Boltzmann distribution curve, as we've shown you before. Concentration is referred to as a effective kinetic concentration in the textbook. When I talk about kinetic concentrations, in a reaction, reactants must be able to find one another. What that means. For example, if this room had some A's and B's in it that were going to react to produce product, if I had an A in the back room corner and a B in the front room corner, then the probability of those finding one another is very low. But if I fill up the room with A's and B's, it'd be a little more effective in one finding the other and interacting. And that's what's called an effective kinetic concentration. Effective collisions, orientation factor. Molecules are three-dimensional entities that have a certain three-dimensional interaction in order to react, a stereochemical interaction. And in doing so, if they don't hit in just the right arrangement, it's like my hands, if back of my wrist bump together, I don't get a reaction. But if they enter finger lock, that's the only way I can say hold them together. But any other way, they wouldn't react. By increasing temperature, you increase the velocity and the number of collisions, and they certainly increase the probability of those two particles colliding in the right orientation and sticking together. So orientation and collision, highest probability at delta EA. So it's just a point at which the majority of the particle interactions are occurring, and this probably maxes out at the activation energy. Now it continues to react, but one of the things about this issue in the Boltzmann distribution, as particles generate products, the reaction rate begins to decrease, because particles then lose ability to find one another, and so it's kind of a fine line in that context. In nature, you must have reactive reagents. They must be able to react, or else you won't get a product. Temperature refers to you have to have the particles at or above the activation energy. So when we talk about the kinetic molecular theory, it leads to the collision theory, which says that in the collision theory, 4 factors must come together, C, E, and T, in order for products to be generated. Now, the transition state theory is just a graphic representation of reaction progress and energies of the reactants against the products that are generated. Now you have 2 types of graphs that you need to understand. One is based upon an exothermic reaction, and the other is on endo, and I'll show you that in just a moment after we do the exothermic. So a graphic like a transition state curve is a two-dimensional plot. On the horizontal axis is reaction progress. So as the reaction progresses through whatever it's going to do to produce products, it starts with a certain internal energy. Now, on this vertical axis, this would be potential energy. Well, I'm not going to identify it. Anyway, if we're talking about an exothermic reaction, what you have to understand, and I think you already know, is that the reactants produce products plus heat. In other words, the products are at a lower energy level than the reactants. So what we do is we start off with what are the reactant energy levels. And so up on this line, this potential energy line, is if we have A plus B going to products, reactants going to products, then A and B have a certain amount of energy content, what you call internal energy, and you can calculate that easy enough looking at standard heats of formation. And we call that, I call it, what we call a positional energy of the reactants. And I'm going to put ER right there. And you might want to make a note, ER is positional. Reactants. After the reaction has produced products, then the products have an energy level below that of the reactants, EP. That's R. In progress of that reaction and driving it to completion, the reaction progress as it proceeds goes through an energy change sequence that looks like this. Every reaction must go through this. Like this. This portion of it right here, I'm going to move this down so you can get a better graphic here. There we go. There we go. This point here is raising the reaction to the activation energy. And so this is delta EA for that particular reaction. And every reaction has an activation energy, whether it ends up as exothermic, positional energy, or endothermic, which we'll see in a minute. It'll end up over here above the positional energy of the reactant. Okay, so this is your EA point of position, and this is called the reactive intermediate. And you can learn about that if you go to organic chemistry. It is a short-lived structure that decomposes either to products or goes back down the hill to the left to the reactant side of the, and of course everybody wants products, so we push it to you do things to push things to the product side. Well, as it falls, this space here has a certain amount of energy loss, But that happens to be the what we call the activation energy for the reverse reaction. This one going forward is called the forward activation energy. Now, the distance between the positional energies is the heat of reaction, just simply or delta E of the reaction here to here. And you'll notice in the split this in half, this transition state curve, potential energy curve as some people call it, a reaction progress curve, the sum of the activation energy, EA forward, plus delta E of the reaction equals delta E reverse. Okay? Now that's just how to read the equation and the as it relates to here. Now, the same kind of curve, but the end of the curve winds up above the energy content of the reactants, like this. So if we start with the energy content of the reactants and proceed to the activation energy like this, but when it decomposes, the complex, activation complex decomposes, your products wind up here. And so if we extrapolate back here, this is your product level energy. Now, the forward reaction now here is delta EA forward from here, from the reactants, like that. Whereas the delta EA reverse is from here to here, and the delta E of the reaction itself is there. And if you split this in half, of course you got energy, reaction, progress, and energy, potential energy here. You see that the sum of energies is on the right side of this vertical line. That is delta EA reverse, well, let's say just forward, is equal to the sum of those two, delta EA reverse plus delta EA of the reaction. It's just the delta EA of reaction just moves back and forth between the where the position of the term is in this equation. Okay, so what kind of problems are associated with this? Well, you'll typically be given two of the three energies that you need to make your calculation, and you calculate the third one of the three, given two. The problem with this is remembering the endo-exo type curve and how the energy numbers are positioned in this curve. Okay, so if from your worksheet, okay, yeah, you may not be able to see it. Sketch a potential energy diagram for this nitric oxide ozone reaction here. The activation energy for the forward reaction is 10 kilojoules, and the delta H of the reaction is a minus 200. What is the activation energy for the reverse reaction? So for this problem, you start out with recognizing this is an exothermic reaction. And how you draw this is irrelevant, but just as long as the products are below the reactants. So we start out at, say, 10 kilojoule forward activation energy, start here, and then you go up to, say, right there, and then you come back over so that it shows kind of a graphic like that. Now that's exothermic trend. Split it in half like this, and this is 10 kilojoules up to the activation point right there. and it's asking for what is the delta E a reverse reaction. If you were going to push it back over the hill, so to speak, what would this value be? Well, if you look at this distance versus the reaction side, the left side, this represents the difference between the products and the reactants is your heat of reaction. And so that was 200. Now, yeah, it's listed as a negative value, and that's what is supposed to be listed. But when you're working these problems, the sum of these two equals that activation energy. Because of its linear kind of distances, these two add up to whatever that length is for the activation energy. So delta EA for this problem is 10 plus 200. Don't subtract it in this case. And so that's 210 kilojoules is the answer. And you'll have to make that decision. Look at the next one. And it shows the same kind of problem, but for an indoor. So in this case, we'll have the same issue. We want to draw a hypothetical curve for that reaction. Sketch potential energy diagram for this reaction shown. The activation energy for the forward reaction is 251 kilojoules, and the delta H of the reaction is, it doesn't have a symbol before it, so it's plus 176. That means it's endo. So you want to draw a hypothetical graphic transition state curve that shows up with the products above the reactants, like that, and then fill in the values of what you need. So the potential energy is 251 kilojoules for the forward reaction. Delta H of reaction is 176 kilojoules, which is the difference between the levels of the reactants and products. And so what's left is the delta EA reverse. Well, in this case, the A reverse plus the delta H of reaction is equal to the distance over here at the forward activation energy. So they want to know this one. So we see 251 kilojoules is equal to delta EA for the reverse reaction plus 176 kilojoules, which means you subtract 176 from both sides. The 251 minus 176, everything's in kilojoules, whatever that comes out to be. Kilojoules. So you will have one of each of those on the exam. Of course, it's easy enough, but you've got to remember who's endothermic, who's exothermic. Now there are problems that relate the rate constant and temperature and energy values associated with a chemical reaction. It's called the Arrhenius equation. This is developed based upon an equation called the Arrhenius equation that looks like this. The rate of reaction, being the rate constant, is equal to a proportionality constant, A, E to the minus delta EA, which is the activation energy, over the RT value R is a gas constant, and T is a temperature. Well, if you change temperature for a reaction, you change the rate. So we can have two of these, K1 at temperature 1 and K2 at temperature 2. So you can set up one with temperature 1 and 2 into this equation and 2 and add them simultaneously. What you get is the working equation of the Arrhenius equation, and it looks like this. Ln of K2 over K1 is equal to delta E activation energy over R. This is taking all the fluff out of this. T2 minus T1 over T1 times T2. Now, some of you that had me last semester will remember this was presented in the form of vapor pressures in the Arrhenius equation back in gas laws. But this one relates temperature to reaction rates, and this is activation energy. Now, if you look in your worksheets, this is the kind of problem you have. One type of problem will ask you to calculate the activation energy given your rates and your temperatures. And a second type of problem will ask you to say, well, what is the rate constant if you change the temperature from 1 to the second temperature in there. So let's look at that and see how that works. Here, in which they say, in a series of experiments on decomposition of dinitrogen monoxide, rate constants were determined at two different temperatures. Okay, so you're given K1 to equal 1.4 times 10 to the minus 4. I like to set it up like this. At T1 equals 35 degrees C, and you add 273 to that, 8, 7, 8, 9, 10, 308. That's the temperature values in that equation. I'm going to bring the equation back down here. There you go. Okay, so what we're looking at is a K1 and temperature 1. Okay. And then at 45 degrees, let's see, 5 times 10 to the minus 4. So K2 is 5 times 10 to the minus 4 per second at T2, 45 degrees C, which is 318 Kelvin. Right there. What's the activation energy? Well, the R value in here is only the other thing I need to emphasize here. In working with this equation, it's a thermodynamic outcome is what you're looking for. So you have to use the thermodynamic form of the R value, and it's in joules per mole Kelvin. 8.314 joules per mole Kelvin. And this will be published on the reference sheet, the back of your reference sheet. And you will need to use this in kilojoules, which is 0.008314 kilojoules per mole Kelvin. And so for the problem, delta E activation energy is the unknown, and so we need to take this expression, substitute this data, and grind it out to that one. Now I think the second one asks you to get the what's the rate constant at 55 degrees. So I'll go through both of those to try to give you a heads up. So we have Ln of K2 over K1, delta EA over R, T2 minus T1. Actually, what they'll publish is 1 over T1 minus 1 over T2 or something like that. This, to me, is much easier to work with. So I want to solve for delta EA, which is R Ln of K2 over K1. That's T1 times T2 when you manipulate it, T2 minus T1. So we substitute 0.00814 It's all going to come out in kilojoules anyway. And this is ln of K2 over K1, so K2 is 5 times 10 to the minus 4 over 1 times 10 to the minus 4. Put that in here like that. And then T1, T2, so that's 308 Kelvin times 318 Kelvin, divided by the difference in those two. 318 minus 308. And everything comes out in kilojoules per mole. It'll always come out in that. And so it's more of a chug and plug and chug type problem. Let's see, 5 times 10 to the minus 4. Well, the minus 4s drop out real quick, so it's 5 ln number times 0.008314 times 308 times 318 divided by 10, and I get 131 kilojoules per mole. And that's the long and the short of that is just memorize the equation, plug it, and solve it for the unknown. Now, the second half of the problem is the same, is to take this activation energy, plug it into the original expression, and let's get a K2. I'll call it K3. So it doesn't matter which one of the K values. So K1 was 1.4 times 10 to the minus 4 per second, and T1 equal, well, that's 308 Kelvin. Well, K2 is equal to the unknown at, well, let's make it K3, since we already got a 2. And T3 is equal to 55 plus that, 45, 55. That's 328 Kelvin. So we went up 20 degrees. So in that particular case, using the 131 for delta 8, we have, again, the ln of K2 over K1 delta EA over R, T2 minus T1 over T1 T2, like this. And so we're trying to solve for a K2. Well, logarithmic ratios are nothing more than are exponential ratios, so we want to take the difference. So that's what this will give you right here, and then it's equal to the delta EA over R, T2 minus T1, T1, T2, and yada yada yada, like that. So no big deal. Now solve for ln of K2 to equal ln of K1, whatever you have given, it's here, plus, again, delta EA, which is 131, or T2 minus T1 over T1 T2. So it's a computation based on that formula, and it's just asking you to substitute and solve. So ln of K2 is ln of 1.4 times 10 to the minus 4 per second. I'm not going to put the units in right now. That's 131 over 0.008314. That's 328 minus 308 divided by 328 times 308. So it's plug and chug. So let's do that one. 328 minus 308 divided by 328 divided by 308 times 131 equals 0.008314. Okay, and so ln of 1.4 times 10 to the minus 4 plus 3.12 is what I got for all of this computation over here. Y'all correct if I'm wrong. Store 1 clear. 1.4, 10 to the minus 4. Hit my logarithm button. That's 8.87. Minus 8.87 plus 3.12, and that gives us, move that up, plus 3.12, that's negative 5.75. Now remember, that is an ln of K2. So what you're looking at is taking the analog of this, which is e to the minus 5.75, and that's your, I keep doing that. So, second e to the x, second scientific, I got 3.2 times 10 to the minus 3 per second, which is a nice increase from the, well, I'll put it up here. So if you're at 308, you have this rate, which is smaller than this rate. So it increases whatever the differential is, I mean the ratio is. Let me see how much it jumps. 1.4. Jumps 22 times. So reaction rate increases about 22 times from 308 or 35 degrees to 55 degrees. So it's a comparative analysis anyway. So it's a real widely used analysis if you're comparing how to design your reactors and reaction rates so they achieve maximum output like that. Chemical kinetics. Is a study of rate of reactions or reaction rates, and these are examined or studied or described in terms of what we call rate laws, which are proportional to a function of rate factors. And these rate factors are defined by a set of a little acronym that I gave you, CANTC. And each one of these has a meaning: concentration, effects, area, nature, temperature, catalyst, and so forth, like that. So what we do is we make changes in concentration or changes in surface area and look at how the reaction rates change, or change in the structure of the compounds, or change temperatures we just showed you, and see what the reaction rates do. Oh, I forgot the catalyst, and I need to teach you about it. It's real straight up. So these applied to give rate, well, simply rate in terms of those rate factors. Now, each one of these had, well, the ones we worked on were here and, of course, here. Concentration effects required you to understand, I don't know, rate averaging, coefficients, experimental rate laws. I derived the integrated rate laws, but we'll just use first order decay equation. And don't forget the half-life, or 0.693 equals kT to the 1/2. So those two need to be understood and used as we go along. We only mentioned these two. Area, if you increase area, you increase reaction rates because there's more available reaction space, surface. Nature is the structure, chemical structure. We mentioned T-butyl chloride, and this will be Monday. I'll show you this differential versus T-butyl bromide. How do reaction rates change if you change one of the halides in there? And so the bond of chloride to the T-butyl group versus the bond of bromide to the T-butyl group has different bond energies, and one ionizes faster than the other, and that affects the rates of reaction. That's what we're talking about in terms of nature. You compare two compounds that have similar structures except for one functional group, say chlorine versus bromide. Then we finished so far. We'll go to catalyst here in a second. We talked about temperature effects, and that involved the collision theory, and in that collision theory it emphasizes the idea of reaction factors, which is the CENT acronym. Don't get it confused with the rate factors, which is concentration, effective collisions, nature, and temperature energy effects. So, and this relates to delta E activation energies. So it relates to the activation energy. It's the greatest probability of these components coming together simultaneously to generate product. And we looked at transition state theories, which are endo and exo transition state curves. And you'll have to calculate with given two energies, you'll have to calculate the third. But the big issue is for an endothermic reaction, you want to remember to draw it like this, and for an exothermic reaction, you want to be sure to draw it like that. And then split it in half, and then you identify the activation energy, forward reaction, reverse reaction, and the heat of reaction on that, and just add them together as needed. Okay, then the Arrhenius equation, yeah, you got to memorize it. I'm not going to print it on the test. And that's K2 over K1 to equal delta E activation energy over R, T2 minus T1 over T1 times T2. Two calculations, one for activation energy and one find, given the activation energy, find a rate constant. So that kind of summarizes real quick what we did over kinetics to this point. Now, to finish, let me give you a summary of catalytic effects. A catalyst functions to change reaction rate by changing activation energy. In a transition state curve that we've shown you, say a given reaction is, say, an exothermic reaction. Let's see if I can. And follows this trend. Products, and of course, reactants start right there. Now, this is the black curve, I'm going to draw them in color, represents the normal transition state curve. And, of course, this is reaction progress. And these are potential energies for that. And say this was the normal curve. For a normal curve, the rate is given by A E to the delta E A over RT minus delta E A over RT. Now, what I'm fixing to show you is this term right here, the delta EA. If you increase that term or decrease this term, how does it affect the K value? Okay, what do I mean by changing the delta EA in this reaction? Let's say you have a catalyst and you want to speed up your reaction. Now, we're not talking about any specific kind of structure. That's a whole science by itself. But if you wanted to speed up a reaction, what would you have to do to activation energy? You would have to make a lower hill so that whatever happens in the reaction progress, you have to lower the activation energy. So it's a lower hill to roll over. Yes? Okay, so if you want a faster reaction, you want to raise that hill, and we'll just call the blue line a catalyst that functions to raise the activation energy, like this. And so the blue line is a higher delta EA, slower reaction. Well, this can be related in that expression. So if we take that equation and just focus on what this is telling you, this term right here is negative, and R and T and A are constants in this. So what we'll do is just say let K equal E to the minus X, like that. Okay, so you have really two considerations here. Increasing X. So if you increased X by increasing this, what happens to K? Well, this is actually a 1 over e to the x, which is reciprocal. And so you're making this bigger. What happens to K? So if you increase the size in here by increasing this right here, increasing X, that slows reaction rate because it's making a higher hill. So the rate K is lower because you increase X. Well, the same issue is decreasing X increases reaction rate. Because what happens if you decrease this number? Okay, if it gets smaller, this approaches back to a larger number, 1 anyway. in this ratio, so K would speed up. So one quiz question, and there's a couple of questions on the exam that deal with that. Under the circumstances, if you changed activation energy and you had a catalyst that speeded up reaction, what would happen to the activation energy? And it's kind of a qualitative kind of outcome. But catalysts function to increase or decrease or change the rate of reaction. Now, a catalyst, there's a couple of factoids you need to remember, and I think you already know some of them. One, catalysts are not consumed in the reaction, they only change the reaction rate. And a catalyst that speeds up the reaction is typically called an accelerator. And of course, a catalyst that decreases rate is called an inhibitor or a retarding agent. Or rate retarding. So those are just some terms that are typically applied. Catalysts are sometimes misinterpreted as something that speeds up a reaction. Well, there are catalysts that do that. And there are a lot of research going into making catalysts that will speed a reaction up. But you also want to develop systems that slow reactions down. For example, corrosion. Paint and coatings are examples of systems that slow reactions down, oxidation reactions, and maybe classified as retarding agent in terms of catalysts. At any rate, it just keeps the corroding factors from coming into contact or prevents the retarding agents in it from coming together that would slow a reaction and makes it run faster. But that's the long and the short of how catalysts function, and I just wanted to share that with you. It's qualitative in most, except for the equation. What happens if you change the activation energy? And I showed you how that equation defines that effect. Okay.